Some other things that we can consider with the simple harmonic motion as we evaluate the motion here. We look at displacement again measured from the equilibrium point. The amplitude itself is the maximum displacement from equilibrium. A full cycle is to and fro, right? So it's got to go all the way there, all the way back. So if we started our timer here, right, it's got to go all the way there and then all the way back, and then you stop the time. The period is the time for that one cycle, and then the frequency is how many cycles per second. Now, again, it may be slower, right, than a cycle per second, and then we would have a portion of that. But if it's multiple times every second, we would count those up, and that would be how many hertz that we have. If we did, how many cycles per second. And so any vibrating system, we know that the restoring force is proportional to the negative of the displacement, right? So again, the further it's displaced from equilibrium, the more force there is trying to bring it back. We know for the spring constant, again, it's, how many Newton. All right, so let's go ahead and check your understanding here. Let's draw a horizontal mass system. And we'll draw the mass being stretched out 4 centimeters to the right. Let's say it's held there. What kind of energy does it have, and how would you calculate that? And then what would happen to the energy at the midway point? And then B, what would happen to the energy at the condensed point? So I'm going to have you go ahead and try that. And so we know that, yeah, well, we can draw it out here. We're going to stretch it 4 centimeters to the right. So you can draw it be, this is stretched over here. Now it's over here. And go ahead and write down what kind of energy it has, and then how you would calculate that energy. And then what would happen to the energy at the midpoint. So write that down as well. And then what would happen when it's all the way condensed over here. And we'll make sure that you're doing okay. So go ahead and pause the clip, write those out. And when you're ready to check, you can hit play to continue. Okay, so when it's stretched all the way over here, right, it's all potential energy, all spring potential energy, 1/2 kx squared. And the energy in the middle, all kinetic, right? No potential energy, it's not stretched or compressed. The spring, right, is not stretched or compressed. And then the energy at all the way condensed point is, again, all potential energy, right? Because, it's not moving there. The spring is compressed all the way. Again, with spring potential energy, 1/2 kx squared, how we calculate that. And so we measure, how far is it from equilibrium, and depending on that, we calculate the potential energy of the spring. So let's go ahead and just practice a simple one here. Let's say we stretch a mass 6 centimeters, which you're going to need to convert to meters. We know the spring constant. Go ahead and calculate the elastic potential energy of the system if it's stretched, to the right. All right, so we should get 0.063 joules for the energy as it's. All right, so let's take a look at this situation. We have a car that's the top of a 4-degree incline, and it's starting with a speed of 5 meters per second. And let's say, okay, so we got our car, so we can draw that out. And it's starting already with a V initial of 5 meters per second. And it goes for 15 meters on the track. And then at the end of the track, we'll say that this car hits a spring. Okay, and it compresses the spring, okay? And it compresses the spring with 3 meters. Right, and so we want to figure out, what is K for the spring. Now, what we're going to assume, and this is a huge assumption here, right? There's not going to be any non-conservative work is going to be 0. So when you set up your conservation of energy, non-conservative work will end up being 0. So let's go ahead and try this, where you set up your non-conservative work, and in this case, we start with kinetic energy, right? and gravitational energy, and then we end up with elastic and non-conservative work is 0. So let's see if you can figure it out. How much, or what is K for the spring as it's compressed? So go ahead and pause the clip, give it a shot, and when you're ready to check, you can hit play to continue. All right, so we should end up getting, for our height, 9.642 meters. So that's the height. So that's MGH initial. And, it compresses it, and we end up getting 30.908.12 meters for the compressed spring. And that is the spring constant for the spring. Okay, so for energy in a simple harmonic oscillator, we're dealing with the potential energy as well as kinetic energy. And so the potential energy is 1/2 kx squared. The total amount of energy of the system will be 1/2 mv squared. So we add them both up to get the total amount of energy. And so, we have the total amount of energy. We know it's conserved. So in other words, if the spring is stretched way, way out, let's say this is equilibrium, it's stretched way out here, it's all potential, right? In the middle, it would all be kinetic, but somewhere in between, it would be in between, the kinetic and potential. So the total amount of energy doesn't change, though. Over here, it's all potential, and here it's all kinetic, and then here it's a combination of the two. So if we know that, we know the total amount of energy, and we know how fast it's going, for instance, we can figure out, where's the location. Or, if we know the location, we know the spring constant, we know the total amount of energy, we can figure out how fast it's going at a certain point. Okay, so let's take a look at this one here. We have a mass system, 0.4 kilogram mass attached to a 74 Newton per meter spring. And the spring is stretched out 7 centimeters, and we want to find the velocity of the spring in equilibrium. So yeah, based on what we just did, right? We know it's all potential energy of the spring out here, and if we were to calculate that, we end up getting 1/2 times 74 Newton meters times 0.07 meters squared, and that's that many joules. And so yeah, why don't you go ahead and complete this? Go ahead and figure out what the velocity is in the middle. And you can hit pause, and then when ready to check, you can hit play to continue. Okay, so in the middle, it's all kinetic. Therefore, we know the energy. If it's there's no energy lost through friction or air resistance, or thermal energy in the spring, it'll stay the same. And so in the middle, it should be going 0.952 meters per second. So here's a progression of the mass spring system, where in the first one, it's all potential energy. Here's the equilibrium point. But the mass is over here. It's all potential energy. And then in the middle here, it's all kinetic energy. And then, way stretched out here, it's all potential energy. And then in between, right, in between, you've got a combination of potential and kinetic energy. So it just depends on the part where it's at, how much energy it has and the breakdown. And in terms of the total amount of energy, right, if it's at full amplitude, right, and that capital A stands for amplitude, if it's at full